This demo describes the implementation of a driver state monitoring module on a reconfigurable hardware platform. A preliminary demo has been uploaded in the SDALab YouTube channel a year ago, and it can be accessed from the link you can see here. It demonstrates the developed Ubuntu and FPGA frameworks where the DSM module was developed and tested. The motivation for the implementation of the FPGA DSM module is to demonstrate hardware acceleration based on the XRT library, the optimal hardware-software partitioning based on alternative implementations of the same task listed in the library of hardware-software components, and the dynamic reconfiguration of the hardware-software components that is triggered by external environmental conditions, for example, driver gender or lighting conditions. It is based on the ensemble of regression trees machine learning shape alignment method, and this ERT method is adopted by the deformable shape tracking, DEST in short, open source software package, as well as the popular dlib library. This DSM module was developed mainly in the context of 4.1 and 5.1 tasks. The development of the DSM module started by porting the DEST suite of applications to an Ubuntu x64 environment, optimizing the software in terms of speed. More specifically, time-consuming eigencalls were replaced by fast C implementations, with speed increase by approximately 240 times. Alternative shape alignment algorithms and modifications can be easily tested since the compilation and deployment of the application is fast. The results can be directly displayed on screen for easier debugging. A camera or a stored video can be used as input. The GNU compilers are compatible with the target platform. In this environment, we trained a number of alternative ERT models with different number of cascade stages, regressor trees and tree depths, reference pixels, etc. Then the DEST suite was ported from Ubuntu to the target ZyncMP UltraScale platform, which can be installed inside the vehicle. Hardware acceleration techniques were applied. Input is normally a camera facing the driver, however, a stored video can also be used as input. The results can be used by a higher level application to generate alarms if driver drowsiness is recognized. And no display is normally needed, but the DSM application can store an output video similar to the one produced in the Ubuntu environment, which can be watched offline. Here you can have a glance on the various ERT models that have been trained so far. These models differ from the default in a number of cascade stages, trees, reference pixels, etc. Customized hardware with different features are needed to support each one of these models. Concerning the employed hardware acceleration techniques, a hardware kernel was used to access all the regressor trees of a single ERT cascade stage. Multiple wide ports of 1024 bits are used per argument to accelerate data transfer. The arguments are copied in parallel in local BRAMs. The regressor trees are split in two groups that are processed in parallel. Loop unrolling and pipeline techniques were applied, and thus the frame processing time was reduced from more than 90 milliseconds needed by an ARM A53 processor or a non-optimized hardware kernel to less than 20 milliseconds with an optimized hardware implementation. Concerning the dynamic reconfiguration, two ERT models from the table shown earlier are loaded sequentially, emulating a trigger by a change in the environmental conditions. A fast model with 400 regressor trees and a slower but more accurate model with 600 regressor trees are tested, with a female driver in daytime and a male driver in nighttime, respectively. Different hardware kernels are called in the FPGA, depending on the ERT model loaded by the host software, and both of these kernels have been compiled in the same XCL bin can be retrieved locally or remotely, while alternatively, the kernels may exist in different XCL bins. The application is started from this terminal. The model M11 is loaded, and the day 1 MP4 video is processed. You can see here the output video that is stored in the SD card of the development board after processing 420 frames. Back to the console, we see that M11 reached the frame processing time slightly above 18 milliseconds, while dynamic reconfiguration takes place loading M12 and its kernel. This is the second output video. We see that model 12 and its corresponding hardware kernel is slower since it deploys a larger number of regression trees. EstaLab developed a new dataset displaying drivers in real car environment and nighttime conditions in order to test or train models under these conditions. Thanks for watching.